Okay, let's go ahead and get started. So today what I wanted to do is continue our discussion of renormalization. So last class I sort of worked out in detail some of the aspects of the renormalizability of quantum electrodynamics. We learned that QED is renormalizable. I sort of went through a general argument involving power counting and dimensional analysis. And so I thought what I would do with today is I would begin by sort of reviewing a somewhat simpler example of renormalization, just so that we all are on the same page and that you have another example of renormalization in a quantum field theory to think about. So today I'll just talk a little bit more detail about renormalization in scalar quantum field theories. So this is actually very similar to an exercise that you'll be doing for Friday where you work out the renormalization of Yukawa theory. But today I thought I would just consider a very general class of theories, namely scalar quantum field theories in d dimensions. So here, just schematically, I'm going to leave out my factors of 1/2 and so forth. We're thinking about a scalar field theory. And what I would like to do is I would like to start thinking about renormalization more generally of a theory not where we have a phi cubed interaction, a phi 4 interaction, or something like that, but really where we allow all possible types of interactions. So, for example, that means that we would allow all phi to the n endpoint interactions of phi. And in principle, if we were interested in doing so, we could also add derivative interactions, interactions that involve, say, d squared phi, phi squared, d squared phi quantity squared, phi squared, things like that. Okay, so you could imagine considering a very general class of scalar field theories where we have all possible interaction terms turned on. All interaction terms, say, consistent with Lorentz invariance or with whatever other symmetries we want to add. Okay. And what I would like to do is just discuss a little bit more generally sort of some of the aspects of the renormalizability of this theory, talking about scalar theories and more generally. And this is going to lead us by the end of class today to, I think, a rather different way of thinking about renormalization, namely the Wilsonian approach to renormalization, which is sort of the more modern point of view about renormalization. Okay. So, so the first thing to do is let's just start out with a little dimensional analysis. So the Lagrangian, this quantity in box here, has dimensions of mass to the d power. And so that means that, as we saw last time, our scalar field, so if d phi squared has to have dimension d, d by dx has dimensions of 1/length, that is to say dimensions of mass. So in order for the kinetic term derivative of phi squared to have dimension d, phi has to have dimension d minus 2/2. And so that means that our coupling constant Gn that we've written here has dimension, well, Gn phi to the n has to have dimension d. So our coupling constant Gn has to have dimension d minus the contribution, minus the dimension of phi to the n, which is n times d minus 2/2. Okay. So that's the dimension of this coupling constant G. And last time we saw that in the context of quantum electrodynamics, theories where the coupling constant had positive mass dimension were very different from theories where the coupling constant had negative mass dimension. Okay. In particular, theories where the coupling constant, in the case of electromagnetism, this was the electric charge, had positive mass dimension, were renormalizable, and those where the coupling constant had negative mass dimension were non-renormalizable. So today what I want to do is I want to take that observation one step further. I want to see how this works for more general families of quantum field theories, such as the one that I've written down here, which has an infinite number of possible couplings turned on. And then we'll eventually start thinking about the dynamics of quantum field theories, really the dynamics of spaces of quantum field theories labeled by the different possible values of these couplings G sub n. Okay. So let's start by really redoing the calculation that we did last class, now in the context of scalar field theory with these more general types of interactions. And so what I'd like to do is consider a Feynman diagram. Say, let's call it I. And this Feynman diagram, okay, so it will have some number of external legs, so external phis. It'll have some number of loops that I'll call L. Some number of internal propagators. And finally, there are an infinite number of different types of vertex that are allowed in this theory that are labeled by this index n. And so I'll let V sub n be the number of vertices sort of type n. That is to say, the number of endpoint vertices. So, for example, your diagram, I don't know, it might look something like this. Well, really, the world is your oyster. You can really draw any kind of diagram you want there. Okay, and let's draw a really high order vertex like that. Okay, there's a diagram. If you're allowing all possible types of vertex, then you can really draw absolutely anything you want. So here you can say, well, there's a 3-point vertex, a 3-point vertex, 3-point vertex, 3-point vertex. It looks like I draw mostly 3-point vertices. Okay, that looks like a 5-point vertex right there. Okay, maybe that's a lesson. So, okay, there's a 4-point vertex. Good. Okay, so as before, we want to characterize this diagram by thinking about how divergent it is. And the superficial degree of divergence, that is to say, the number of powers of momentum in the numerator divided minus those in the denominator. Well, if you have a diagram with L loops and you're considering a scalar field theory in D space-time dimensions, you get a d-dimensional integral for each loop. And then you get the propagators have 2 powers of the momentum in the denominator, so the total degree of divergence is d times L minus 2p. And so what we did last class is I gave you, we explicitly thought about the types of vertices that were allowed in quantum electrodynamics and used that to compute D and to categorize which types of diagrams were divergent and which ones weren't. So today, what I'm going to do is I'm going to redo that calculation in a different way, using a sort of much sneakier trick, but one which really makes it clear why it is that the dimension of the coupling constant is responsible for whether a theory is normalizable or not. Okay? That's really, I think, one of the key physical points of sort of this class, and so I think it's worth going through and understanding a bit more physically. Okay. So the first observation is that let's just think about this Feynman diagram I. So this was I. Now, I is a Feynman diagram, which is a shorthand for an integral, an equation. And one of the things we know about this Feynman diagram is that it contributes to an endpoint, a capital endpoint vertex. That is to say, so it must have the same dimensions as the coupling constant G sub n, right? So in the present case for this diagram that I drew up here, we have 5 external legs. So, you know, this is one of the diagrams that would contribute to the set of all diagrams with 5 external legs. And another diagram that contributes with 5 external legs is just the 5-point interaction vertex G sub 5. So that means that our Feynman diagram has to have the same dimensions as the coupling G sub n, which we worked out above is d minus capital N d minus 2 over 2. However, if you think about how this Feynman diagram is defined, this Feynman diagram has L loops, so its degree of divergence, so it has dimension d times L, and p propagators. You lose 2 powers of dimension for each propagator because it has dimensions of 1 over mass squared. And for each vertex, you also have to take into account the fact that you have a coupling constant at that vertex that has a particular dimension. Okay? In particular, if Vn is the number of vertices of type n, then you have to include the coupling constant, the dimension of the coupling constant that you insert at that vertex. So you can then just go ahead and solve that equation for the superficial degree of divergence. That was dl minus 2p. So just comparing this equation with this equation, we see that the degree of divergence is, well, the dimension of the coupling constant G sub capital N minus the sum over n Vn G sub little n. Okay, so let's just stare at that for a second. So this is the equation that we're after. Okay. So this tells us under what circumstances your diagrams can be divergent. Okay. So first, let's think about the following. Okay. So if we have any coupling Gn such with negative dimension, then that means that any diagram will diverge at sufficiently high order in perturbation theory. Why is that? Well, let's say we're studying the 5-point vertex up above, but we have a G sub n which is negative. Then that means that if you look at very high order in perturbation theory, you'll have a lot of vertices V sub n, and this quantity d is eventually going to become very large and positive. So at high order in perturbation theory, any diagram at sufficiently high order will be divergent. Okay. And so that means that the theory is non-renormalizable. On the other hand, if all of the couplings in the theory have positive dimension, then only a finite number of amplitudes diverge. And in particular, then only those amplitudes with G sub capital N being greater than or equal to 0 can possibly diverge. Because as you go higher and higher order in perturbation theory, D is going to get smaller. And so the degree of divergence of a given diagram is going to get lower and lower and lower as you go to higher and higher order in perturbation theory. The exception being if you have a dimensionless coupling constant, then you could have diagrams that are equally divergent at all orders in perturbation theory. And so in particular, what we see is that only a finite number of amplitudes diverge in the theory, and these divergences can be absorbed into a finite number of counterterms. And in particular, the counterterms that they can be absorbed into are the coupling constants G sub capital N. Okay? So, to say that another way, we could say that in a theory with only these positive dimension coefficients turned on, all of the UV divergences can be cured by renormalizing these coefficients. And for each UV divergence that you need to cure, you have a counterterm that you need to fix, and you have a physical condition that you need to impose in order to fix that coefficient. And the corresponding physical conditions can be taken to be really setting the values of these coupling constants at some physical scale. For example, in the case of QED, we set the mass of the electron and the electric charge at some physical scale. For the electric charge, it was convenient to set it at very long wavelength. For the mass of the electron, we set it at some physical mass. And typically what will happen is that if you have a theory where you have one of these couplings turned on with positive mass dimension, all of the counterterms for the couplings with positive mass dimension will need to be included. Or rather, will get non-zero contributions unless they're set to 0 by some symmetry. Is that clear, more or less? So it's sort of useful and I think instructive in the case of a scalar field theory to run through this in a little bit more detail, okay, just so that you can get an idea of the sorts of theories that are renormalizable, what the universe of renormalizable theories looks like. Okay. So for example, let's consider scalar field theories in 4 dimensions. Okay, we live in 4 dimensions. That's pretty interesting. So an interaction that goes like phi to the n with n less than 4 is going to be super renormalizable. So remember that an interaction is super renormalizable if not only are a finite number of amplitudes UV divergent, only a finite number of diagrams get UV divergences. So in particular, you can see, just let's stare at this formula up here for a second. So in this case, so if you have a Gn phi n, here the dimension of Gn, well, what was it? It was d minus n times d minus 2 over 2. So here n is equal to 4, d is equal to 4, so that's going to be 0. I did that correctly. Because 4 is equal to 4. Sorry, I'm looking at not 5/4, I'm looking at less than 5/4, so it's going to be positive. Okay, so the dimension is strictly positive if you're looking at a, say, phi cubed interaction. And so if you look up here at this degree of divergence, you can see that if Gn is equal to 1 or 1/2 or something like that, then as you go higher and higher order in perturbation theory, these diagrams will get more and more convergent. So there are only a finite number of divergent diagrams in the theory. On the other hand, if Gn is equal to 0, as would be the case for a phi-4 interaction, then there'll be an infinite number, or there'll be divergences at all orders in perturbation theory, but there'll still only be a finite number of amplitudes that are divergent. In particular, in phi-4 theory, you'll have the same accident that happened in quantum electrodynamics in 4 dimensions, namely which was that the degree of divergence was independent of the number of vertices. And that's a general feature of a theory with a dimensionless coupling constant. So for example, in phi-4 theory, the theory is renormalizable. And the coupling constant, I guess we often call it lambda, not g, is dimensionless. Yes?
So can you explain again why the dimensionality of the diagram is equal to the dimensionality of the coupling constant?
Let me understand. Okay.
Why dimensionality of I is equal to G?
The dimension. Okay. The point is that two terms that are added must have the same degree of divergence, right? Sorry. Or let me say that a little more. I said that incorrectly. If you want to add two quantities together, they have to have the same dimension.
Okay.
Okay. So imagine taking this 5-point vertex. Imagine computing a 5-point scattering amplitude. What is it? Well, it's equal to a 5-point vertex plus this other diagram that I drew right here, plus a lot of other
But the amplitude
terms.
is just the expectation value, the zeros of the powers of phi.
Yes.
Right? I mean, so what do we have?
You could also, yeah.
But they are not equal, the powers of phi and the powers of G.
Okay, no. Remember that when we write down a scattering amplitude, that's not exactly equal to an endpoint function. You have to strip off the powers of momentum corresponding to the external legs from the LS0 formula. And if you do that, you'll get exactly that answer.
Okay.
I mean, when I said it was equal to G sub n, that was just a quick and dirty way of writing down the answer. You could have also done it by using the LSZ formula, or you could have done it just by counting up the terms in the diagram. And, that's what, last time when I made this argument for QED, I used the fact that I only had a triple interaction vertex, so I could just stare at the vertex and enumerate these vertices explicitly. But here I'm just using a sort of more general argument, because if I tried to do it that way, I actually it gets a little tedious. But yeah, good. Good. Any questions on this so far? I mean, the thing that you need to remember is that coefficients with a positive mass dimension, are safe as far as making your diagrams more divergent. But interactions where the coupling constant has a negative mass dimension are dangerous. They contribute at all orders and make the diagrams more and more UV divergent. It's kind of a miracle, but it's dimensional analysis, which is a miracle, I suppose. Good. So, thinking about scalar field theories in 4 dimensions again, if you have a phi n interaction, say the 5-point interaction that we described above, that's non-renormalizable. So in the space of scalar field theories, there's really just phi cubed theory, phi 4 theory, as far in 4 dimensions, as far as renormalizable interacting theories. Now, pretty soon, perhaps by the end of this class, we're actually going to see that there's nothing particularly bad about non-renormalizable theories. They just don't quite play the same role as renormalizable theories. Now, in studying quantum field theory, of course, we're not just interested in theories in 4 dimensions. We may also be interested in theories in less dimensions. So let's say I'm studying some material system in 2 spatial dimensions that's effectively 2-dimensional, such as a lattice of atoms, and studying the waves propagating on that lattice. So this would be relevant, for example, for a 2-dimensional metal. Then I would be studying quantum field theory in 3 dimensions rather than 4. In that case, the interactions of the form phi n for n less than 6 are going to be renormalizable. So again, just using this formula up here. Whereas the ones with n bigger than 6 are going to be non-renormalizable. In 2 dimensions, actually, life gets even more interesting. Because in 2 dimensions, it turns out that the phi to the n for any n are going to be renormalizable. So the world of 2-dimensional field theories is very different from higher dimensional field theories. And finally, sometimes it's interesting to consider theories in more than 4 dimensions. These are mostly of sort of more formal interest. But for example, if you look in Srednicki's textbook, the example that he really beats to death is the one of 6-dimensional field theory. The reason why that's interesting for him is that in that case, it's the phi cubed theory that is renormalizable. You know, I think the point of view in that textbook is that he wants to study the theory, he spends a lot of time studying phi cubed theory in 6 dimensions because it's renormalizable and it's the simplest possible renormalizable theory because it only has a cubic interaction. So that makes the computation of counter terms and the absorption of the divergences and all like that relatively simple, as you discovered more or less on your problem set. I guess it was the week before last. And then if you go in higher dimension, d bigger than 6, there are no renormalizable interactions. Okay. So all of the interactions where you have some sort of non-trivial interaction, that is to say not just the kinetic term, are going to be non-renormalizable. So when we talk about renormalizable theories, they're really incredibly special and rare objects in a sense, because in the infinite dimensional space of couplings, non-renormalizable theories appear to be very special in the sense that all but a finite number, a handful of the couplings, have to be tuned to be equal to 0. So we sometimes say that non-renormalizable theories are very fine-tuned. Okay. Any questions on that so far? Okay. Let's see.
You mean renormalizable theories are very
renormalizable theories. What did I write there? Renormalizable theories are very fine-tuned. Okay. I mean, so it might be worth, should I do the example of phi 4 theory in 4 dimensions just to remind you of all? Okay. Why don't I do this? It'll just take a few minutes. Just sort of to remind you of how it works. Okay. So, for example, if you have phi to the 4 theory in 4 dimensions, then we saw that this is a renormalizable theory. And the degree of divergence of a diagram is then equal to just, well, I wrote it down up here. Well, I guess so the degree of divergence of the diagram is just G sub n, which is equal to n, so D minus n times D over 2. So that, for example, the only diagram with degree of divergence 4 is equal to the vacuum diagram, which is unobservable. The only diagram with D equals with degree of divergence 3 is the 1-point function. So generally we set that 1-point function equals to 0 by absorbing it in a counter term. But for phi to the 4 theory in 4 dimensions, this is actually 0 because you have a phi to minus phi symmetry. So for example, this is the theory where the Lagrangian is d phi squared plus m squared phi squared plus lambda phi to the 4th. That has a phi to minus phi symmetry. So that means that the expectation value of any odd number of powers of phi in the vacuum state has to be equal to 0, so that this 1-point function has to be equal to 0. So in particular, the 3-point function is also going to be equal to 0. At d equals 2, this 2-point function is non-zero and UV divergent. And as in the case of QED, we can characterize that UV divergence by a finite number of terms. So evaluating this, say, at P is equal to M, or at P is equal to 0, you'll get a quadratic UV divergence. And then Taylor expanding in powers of P, say around P is equal to 0, you'll get something that's logarithmically divergent. And then at higher orders in P, you'll get finite terms. So here we have 2 UV divergences. Which can be absorbed into 2 counter terms. Namely, the wave function renormalization of phi and the mass renormalization. And those 2 counter terms are set by 2 physical conditions, namely that the propagator has a pole at p squared equals m squared, and that the residue of the pole is equal to 1. And then finally, as we mentioned, at d equals 1, you have this 3-point function, which is equal to 0 by symmetry. And the final divergent graph is the one that renormalizes the 4-point function. Okay. So this is going to be logarithmically divergent because the degree of divergence is 0. And this UV divergence is absorbed into the counter term for the lambda phi to the 4th interaction. So at the end of the day, you have 3 divergences, 3 counter terms, and 3 physical conditions that you need to impose. The 3 divergences come from the propagator and the 4-point function. The 3 counter terms are the wave function renormalization, the mass renormalization, and the coupling constant renormalization. And the 3 physical conditions are that you define the renormalized coupling to be the value of the 4-point function at a particular momentum scale. You define the renormalized mass to be the location of the pole in the propagator, and you normalize the field so that the residue of the pole in the propagator is equal to 1. Okay. So For example, okay, just because you can never go through this too many times, the way that we would do this explicitly is you would imagine starting by writing out, say, a bare Lagrangian with a bare field phi naught and coupling constants m naught and lambda naught. And then you would rewrite this in terms of the physical couplings plus some counter terms. So I'll let phi without a knot be the physicals field, m without a knot be the physical mass, and lambda without a knot be the physical coupling. And then you have our wave function renormalization, which multiplies the d phi squared counter term, a mass renormalization, and a coupling constant renormalization. And delta z, delta m, and delta lambda are fixed by, by saying that the propagator has a pole at m squared with residue 1, and likewise that the 4-point function at a particular value of the coupling is equal to lambda. So, and once you go ahead and use those conditions to fix those counter terms, order by order in perturbation theory, you can express all of the physical quantities in the theory in terms of the renormalized values in the coupling. Okay, so this is a procedure that we've gone through several times. We went through it quite explicitly in the case of QED, and we at least talked about it and learned how to do the computations in some other cases. I think that on the problem set this week, I assigned you the task of going through the entire procedure of renormalization, starting from the action, working out all of the counter terms, working out all of the diagrams, imposing physical conditions, and all of that stuff for Yukawa theory. So you'll get practice for doing this all yourself. But at this point, hopefully, all of this should be clear. And at this point, hopefully, everything is now just reduced to some computation. So this really sort of finishes what I wanted to say in this course about, let's say, the old-fashioned approach to renormalization, okay, which involves power counting and distinguishing in this way between renormalizable and non-renormalizable theories. So before I continue on to sort of the more modern perspective on renormalization, let me just pause here and see if there are any questions. Is this procedure, hopefully this procedure is crystal clear to everyone to the point that you could leave class today and go work out that problem on the problem set for Yukawa theory with no problems whatsoever. Are there any questions on this? Good. I mean, really, yeah. I mean, renormalizable quantum field theories are really a remarkable thing because an infinite number of predictions can be made in terms of only a finite number of physical observables, namely the renormalized or physical values of the coupling constants sort of defined at some energy scale. But what I want to emphasize about this is that at this point, the renormalizability of a theory probably appears like a bit of a miracle. In particular, if you think about what's happening when I talk about renormalization, is that we have some physical process that's described by the exchange of some vertical particles or some vertical particles running around in loops. And somehow, the only terms that actually appear in your answer at the end of the day don't involve those virtual particles running around at very high energy. They only involve virtual particles at low energy. Energies of order, say, the energies of your external particles. So virtual particles have momenta that are of the same order as the external momenta. And in particular, it means that if you're studying quantum electrodynamics or hydrodynamics or the weather or anything like that, you don't need to know about QCD. You don't need to know about quantum gravity. You don't need to know about physics at very high energies. Okay? So in particular, for a renormalizable theory, it appears that long-distance physics can be studied independently of short-distance physics. For example, if you had a theory of quantum electrodynamics where when you studied the loops of the virtual electrons, that was dominated by the part of the loop integral where the electrons had very, very high energy, then you wouldn't be able to do things like predict the anomalous magnetic moment of the electron without knowing all of the details of, theories at arbitrarily high energies. Okay? And this is something that's very, that would be, that would be a failure as a theory of physics, because it would mean that you would need to know about QCD in order to predict the weather, right? You would need to know about very short distance physics in order to understand long distance physics. And from the point of view of everything that we've done so far, the fact that QED is renormalizable and you don't need to know about quantum chromodynamics to predict the weather, it appears like a miracle. Okay? There was no sort of underlying way of understanding why it is that there's a theory of the weather or a theory of quantum electrodynamics without a theory of QCD or a theory of quantum gravity. In particular, the miracle was that all of the coupling constants with negative mass dimension happen to be exactly equal to 0. If you write down a random theory, there's no particular reason why, of the infinitude of possible interactions that a scalar field could have or any other field could have, why it is that all but a finite number of those coupling constants are non-zero. So it seems like a miracle, and it seems like something incredibly fine-tuned. And indeed, until the 70s, I think this was the point of view that people had about quantum field theory. They said that, renormalizable theories are special and miraculous. Non-renormalizable theories are bad. Let's not talk about them. They don't make any sense. But in fact, I think the more modern point of view of quantum field theory, which usually goes under the name of the Wilsonian perspective on quantum field theory, is not that renormalizable theories are some miraculous special thing that we're incredibly fortunate to have, but that renormalizable theories are the universal dynamics that describe physics at low energies. In particular, the renormalizable theories that we've been discussing, not just quantum electrodynamics, but all of those scalar field theories that I wrote down for you earlier, the Yukawa theory that you'll be studying in your problem set, are not some special, highly finely tuned object that we were just happened to be so lucky to find ourselves living in, but rather that these are the generic behaviors of theories when you study them at very long distances or very low energies. And there's a sense in which this point of view is much more natural if you think about this from the point of view of statistical mechanics or condensed matter physics than high energy physics. So for example, when we talk about quantum field theory in statistical physics or condensed matter physics, you might imagine, for example, some material that's made up of a lattice of atoms. Okay, you know that in the high energy and the ultraviolet, you have some discrete atomic physics, but at very low energy, you should describe the system by, propagating waves such as phonons or something like that, moving on this lattice of atoms. And so I think what the Wilsonian perspective really does is it takes that sort of more condensed matter point of view and applies it to quantum field theory. And so that's what I wanted to start to do now. Maybe before I dive into this, let me pause and see if there are any questions. No questions? Okay. Okay, so, it's pretty interesting. I mean, even when I was a grad student starting to learn quantum field theory, I think that a lot of the textbooks that I was reading, took this very different point of view about quantum field theory. I'm not so old that nobody was talking about the Wilsonian perspective, but I am old enough that it somehow hadn't percolated into all of the textbooks that I was reading at the time. So if you do look at some of these earlier textbooks, then, they really just say that, well, quantum electrodynamics has to be right because it's the only renormalizable theory that we could write down. And no, that's really not the perspective that we take nowadays. It's really that quantum electrodynamics is right because there are other sorts of terms that appear that govern the dynamics of electrons and photons and so forth. But when you're studying the low energy physics, these terms are simply not relevant. And they're not relevant in a very precise way that we'll discover later on today or next class. So let's just consider a quantum field theory. And in particular, what I'd like to do is I'd like to point out that when we talk about quantum field theories, and this is especially apparent if you think about quantum field theories in the context of condensed matter physics, every quantum field theory comes with it an intrinsic ultraviolet scale, an intrinsic high energy scale, at which the theory breaks down. Okay. Now we haven't actually studied asymptotic freedom in this class, but so because I want these notes to remain correct when we do study asymptotic freedom, I'll put an almost right there. So it turns out there are quantum field theories that do occasionally manage to survive without some need for new ultraviolet physics. But the typical quantum field theory that you might be interested in describing, say if you were describing some material, say a metal, then that's made up of a bunch of atoms, then the intrinsic UV scale at which the theory breaks down would be set by the lattice spacing of the atoms in your metal. So A here would be a lattice spacing. And then the quantum field degrees of freedom would be the phonons that describe the oscillations of these atoms. And it's literally the case that those phonon degrees of freedom simply do not exist at very high energy. Very high energy, the dynamics is something completely different. In a theory of particle physics, say quantum electrodynamics, or the Standard Model, the UV scale would be set by some other high energy scale at which some new dynamics comes in. So, for example, in particle physics, we know that the Standard Model has to break down once you get energies that are of order the Planck scale. It's likely that the Standard Model has new degrees of freedom at energies far below the Planck scale, but it certainly has new degrees of freedom at the Planck scale, namely those of gravity. But in any case, what we want to do is we want to try and use quantum field theory not to study the physics up at this intrinsic scale where the field theory breaks down, but really we are going to be interested in physics at scales, say momentum scales, which are far below this UV cutoff. And then the question, the truly important question, is the physics of the ultraviolet modes, that is to say the high energy modes, say with k of order lambda, or even higher than lambda, important to those at very low energy. So k much less than lambda. So let's just consider a simple example that I'll be analyzing in a bit more detail for the rest of class today. So let's consider again our friendly scalar quantum field theory. And in particular, let's imagine that we have a kinetic term plus a bunch of interaction terms. So here we could have our gn phi to the n interaction terms. I'm largely going to be doing dimensional analysis, so forget all my n factorials and stuff like that. We can even imagine derivative interactions, so say of the form cn d phi squared phi to the n, plus, and then interactions with more derivatives, with the derivatives placed in different ways, and so on and so forth. And one way of studying the theory, say of computing scattering amplitudes or correlation functions, would be to study the partition function, which is a function of the source j that's in the path integral language given by an integral of e to the I L plus j phi. So remember, to compute a correlation function, you just take z of j, take some number of derivatives with respect to j, and then set j equals to 0. And what I would like to do is I would like to think about breaking up this path integral into an integral over ultraviolet physics and an integral over infrared physics, an integral over high energy physics versus low energy physics. So how do I want to do that? Well, when we talk about path integrals in quantum mechanics, say, we often integrate over the space of fields phi of x, that is to say the set of all functions of x. But there's no reason why we couldn't do that integral in Fourier space as opposed to in real space. So any function phi of x can be, functions phi of x are in one-to-one correspondence with their Fourier transforms. So I could certainly write this integral as the product over all momentum modes k times the integral d phi of k, where phi of k is the Fourier mode of our field phi of x, times e to the L plus j phi, where phi of k is the Fourier mode at momentum k of our field phi of x. And we decided that every field theory comes with an ultraviolet cutoff scale above which the theory breaks down. So really what we mean when we write the integral d phi, what we really mean is only integrating over modes below that UV cutoff. So that's very clear if you think about, say, a lattice, where it is just literally the case. You could look at atoms on a lattice, and then for atoms on a lattice, the momentum simply can't take values that are shorter than the lattice spacing. Now, there's one subtlety that I should mention here, which I'm not going to talk about more today, but which we'll have to come back to at some point, which is that strictly speaking, when I talk about this, I should talk about Euclidean signature rather than Lorentzian signature. The reason being that I really want to restrict my energies and momenta to be small. But when I work in terms of a 4 momentum k, if you restrict your 4 momentum k to below some bound, the vector k and the energy k can still be very large, even if k squared, the norm of that 4 vector is small. Okay. So at some point when we go back and do this more precisely, we're going to have to work in Euclidean signature. But for now, I just want to sort of sketch out for you how the argument goes so you can see the general structure. Okay. So let's say that we're interested in some low energy physics. So let's say that we're interested in physics at very low energy. Then that would be, say, the physics of modes with k less than b lambda, where b is just some dimensionless constant that's less than 1. In principle, we're hoping that it's going to be much less than 1, so that the physics of this UV cutoff is not going to become important. Then that means that we really don't care about modes with k bigger than b lambda. And so we only want to compute z of j in momentum space for those modes j of k with k less than b lambda. We only want to compute the the correlation functions, say, of our field operator at very long wavelength. So we could just be a little sloppy and call this JIR, where IR stands for infrared or low energy. So JIR will be equal to J of k for k less than b lambda. So what we want to now do is divide the integral into 2 pieces. So we want to divide it into a UV part, a part that we don't care about, that we're not going to observe, and an infrared part that we will observe. So for example, we really want to take, so we can just relabel our field variable phi in the following way. So what I'll do is I'll define phi UV to be the set of field modes with k, let's see, k bigger than b lambda. Sorry, I'm not writing that clearly. And phi IR to be the set of field modes with k less than b lambda. And then, so this is just a relabeling of our field degrees of freedom. So then, the integral over all field variables with k running from 0 to lambda can be divided into 2 parts. So it's an integral over the IR part and an integral over the UV part. And our goal then is to do the UV integral and be left with some theory in the infrared. That'll be the theory that we actually observe. So so what we need to do then, so we're interested, so let's just take a look at so this is our expression for the partition function. So we have an integral over d phi that we want to divide into a UV and an infrared part. And then we need to ask what happens to this the Lagrangian and the interaction terms that appear in the Lagrangian. So, so the partition function will be an integral, will look like some sort of IR theory. Well, okay. Let's just do this all out a little bit more explicitly. So our goal really is to integrate out those UV degrees of freedom and to write this just as some effective theory in the infrared. This is going to be, L effective is going to be some function only of the infrared degrees of freedom. And J is what I call JIR up above. It's a source that couples only to the infrared degrees of freedom. So I'm not going to actually do that calculation for you today. I just sort of want to sketch for you how it goes, and we'll hopefully be able to do the calculation next class. Roughly speaking, the idea is that you think of L of phi as L of phi infrared plus phi UV. Okay. And L has a kinetic term. Okay. So the kinetic term, and you want to write this as L of phi IR plus L of phi UV plus some sort of interaction term that mixes the two. And then you want to do the UV integral. And that'll give you some corrections to the IR physics. So for example, the kinetic term, d phi squared, well, what is that? That's d phi IR squared plus d phi UV squared. And then you might think that there's a cross term, d phi IR times d phi UV. That's actually equal to 0. Does anybody see why that's equal to 0?
Oh, it's because the IR nodes and UV nodes are applied.
That's right. That's exactly right. Yeah. So so there's no mixing term. And just to say that a little differently, if you wrote down a mixing term that looked like integral dx of d phi IR times d phi UV, and then you just inserted the Fourier transform, then so that this was an integral dk e to the I kx. It would be a k mu phi of k. That would be a phi IR of k. And likewise for phi UV. The fact that phi IR is non-zero only for k less than b lambda, phi UV is non-zero only for k bigger than b lambda, you would just get 0 for this integral. However, the same is not true when you consider higher order interactions. So for example, phi fourth, you'll get terms that look like phi IR to the fourth plus phi IR cubed, phi UV, and so on and so forth. So you'll get a plethora of interaction terms that describe the couplings between the UV and the IR modes. And so what you'll be left with is an expression for the partition function, now regarded only as a function of the source that couples to the IR modes, because those are the only ones that we're interested in, which is an integral d phi IR times e to the times your usual Lagrangian, your original Lagrangian, regarded as a function of phi IR. plus the coupling, j phi. And then we have to do the UV path, part of the path integral. So we get an integral L of phi UV plus these various interaction terms. And probably what we'll do next class, is we'll try to actually do this UV path integral. And the result, we're going to try and write as a quantum field theory that governs just the infrared modes. So the result, so if you just do the UV path integral, the result is going to be expressible as some field theory just for the infrared degrees of freedom. So if you like, you could take this expression as the definition of L effective. So L effective is defined to be whatever you get when you integrate out all of the UV degrees of freedom. So let me just sort of summarize a little bit what's going on here. Yes?
Can we also do the same with the IR? You integrate out the IR and try to L effective for the UV?
Yeah, you tend to get very problematic things happening when you actually do the calculation if you do it that way. Okay? The reason you tend to get all sorts, yeah. So in principle, you could think about doing that. In practice, that's not what we tend to do.
What is the problem?
Well, the problem is really that you get IR divergences of the sort that we encountered earlier when we considered our massless degrees of theory, when we considered soft photons and soft particles with zero mass squared. Let's put it this way. If you're only interested in the ultraviolet physics, and then you're free to integrate out the infrared physics, but as we're going to see, when you do what we do, integrate out the UV and look at the infrared physics, you tend to get universal answers. In particular, you have the structure of a renormalizable theory. You know, what we're going to argue, what we're going to see, is that when you study only the low energy dynamics of a quantum field theory, you sort of automatically land on these renormalizable field theories. Okay? So you tend to get a structure that you can use to make do computations all on its own. But if you try and integrate out the IR degrees of freedom and work your way up to the UV, the exact opposite happens. And so the theory is much less sort of useful. I mean, there's no reason why you couldn't do it in principle. I mean, you could certainly write down an expression for what you get, but it's not going to be as useful. I'm not sure if that was a complete answer to your question. Good. Okay. I mean, there's an important point here, okay, which is that, you know, we have two different things that we're studying. You can either study the full partition function, where you integrate over all field degrees of freedom of e to the integral of L plus j phi. Okay. Or you can study this effective theory, where you explicitly integrate out the UV degrees of freedom. And the important point is that we could use either our original theory or the low energy effective theory to compute the low energy observables. Namely, to compute, say, the correlation functions of the long wavelength modes of our field problem. And the only difference is really a point of view, a difference of perspective. So when we compute using L of phi, we have not integrated out the UV degrees of freedom. And so the modes of the field phi at very high energy are dynamical variables in that theory and appear in loops. So they appear in loops and contribute to observables. However, when we compute using the low energy effective dynamics, we have integrated over the UV degrees of freedom. So often we abbreviate that by saying we've integrated out the UV degrees of freedom. Those degrees of freedom are no longer in the theory. And this integrating out has changed the coupling constants of the theory. In particular, L effective of phi IR is not the same as our original Lagrangian. Because there are all of these coupling terms, like the ones that we wrote down up here, between phi IR and phi UV. So when you actually do this integral right here, you're going to change the answer that you get for the Lagrangian. L effective is just not going to be L. Okay? So that means that in L effective, the effect of loops in phi UV appear implicitly into the low energy couplings. So there are really two different, so really when we integrate out when we decide not to measure UV degrees of freedom, we're free to integrate out those degrees of freedom. And the only effect of these UV degrees of freedom is that it's going to change the values of the coupling constants that we had in the theory. So if you start, say, with a bare Lagrangian with some naive values of the coupling constant for the theory defined at all energy scales, you integrate out the UV degrees of freedom and you get some effective theory in the infrared, which has different values of couplings that differ from the bare values of the couplings. And hopefully, hopefully this is sounding at least a little bit familiar, similar to what we did when we studied renormalization earlier. In particular, if you take the coupling, the UV cutoff scale lambda to be very large, then you may get divergences in these loop integrals. But of course, the only way these divergences are going to enter is through the values of certain coupling constants in the infrared. And you fix those using infrared physics, and then all of the divergences will cancel. Question?
Yes, so this calculation is valid for every Lagrangian.
Yes, that's right. I mean, well, I haven't really done a calculation, so, but I'm sketching, the sketch is about, yeah.
We're going
right.
this with the general Lagrangian.
Well, I mean, what we're going to do is, right now what I'm going to do is sort of finish this discussion and just tell you how you decide based on scaling symmetry which terms are going to be relevant in the infrared physics. And starting next class, we'll try and do some actual computations. So, schematically, what sort of answer do you expect for this effective Lagrangian? So roughly, the effective Lagrangian, well, maybe I'll call it the effective action, so that I can explicitly include the loop variable, is going to be a function of my infrared modes. And, well, what do we expect? Well, just as for all of the quantities that we've been computing so far in this class, where we include the UV portion of the integrals, we expect that that integrating out the UV degrees of freedom will lead to some changes in the effective couplings in the infrared. So, for example, we expect that there'll be some wave function renormalization. I guess we call it delta Z, contributing to the kinetic term, along with various coupling constant renormalizations that we could call delta GN. Plus dot dot dot. Where delta Z and delta G sub n would be computed by working order by order in perturbation theory, at least when your coupling constants are small. And next class we'll begin to develop some techniques for computing these things. Okay. So what we want to do is we want to understand how these coupling constants change as you dial that parameter B. So we want to compare the couplings in the IR theory, the infrared effective theory, to those in the original theory. Now, unfortunately, if you think about it, we can't really just compare this effective action that I've written here to the original action that we had for the theory. The reason being that these are theories that are defined for different sets of dynamical degrees of freedom. In particular, phi IR is defined only for modes with wavelength less than b times lambda, whereas phi is defined over all energy scales running from energy 0 up to lambda. So if we wish to compare these two theories, what you need to do is you need to rescale your variables so that the action S effective is defined over the same range of field values as your original action. So in particular, what we need to do, well, you need to rescale your momenta by a factor of b. And that means that you need to rescale your positions by a factor of b. So what we're doing here is we're going to integrate out all of our degrees of freedom down to some scale, and then we're going to rescale our spatial variables. We're just going to do a change of variables in order to turn the range of field variables that we're looking at back to our original range. So we're going to rescale. So we're going to let x prime be x over b, so that the conjugate momenta k prime is b times k, so that if, sorry, let me do it the other way around. Let's call this x times b, so that k prime is k over b, so that if k runs from 0 up to b lambda, k prime will run from 0 up to lambda. And then we can rewrite S effective of phi IR in the x prime variable. So here I'm really not doing anything except changing the integration variable. So I'll write it as d dx prime. So you get a power of b to the minus d from the integration variable. And you get a 1/2 1 plus delta z. You get a power of b to the minus 2, or is it b squared? Okay. Coming from the d by d x mu. So if I turn that into a d by d x prime mu, you get a power of b squared. And then, well, this guy just goes along for the ride. Okay. And so what we want to do is compare this to our, so now phi infrared, regarded as a function of x prime rather than x, takes values where the moment is non-zero when the momenta k prime runs from 0 up to lambda. And we want to compare this to our original theory. So we have these factors of B and the wave function or normalization out front. So what we want to do then is define phi prime to be B to the, let's see, 2 minus d over 2. And then we want to remove this wave function or normalization piece times phi infrared, so that this effective action will then take exactly the form that you want for a standard I guess I call that phi prime, for a standard field with a canonically normalized kinetic term. And then we'll just call the coefficient of the interaction term Gn prime. So here, for Gn prime is equal to, so let me just make sure that I get this right. So it's just equal to this term up here, but we need to include our definition of phi prime and the various powers of B. So you get a 1 plus delta z to the minus 1/2, sorry, to the minus n over 2, because we have a phi to the n right there. And then we have Gn plus delta n. And then we get B to the power minus d plus n times d minus 2 over 2, if I did that correctly. And hopefully you'll recognize this from the beginning of the lecture. What is that? That's B to the minus dimension of the coupling constant Gn. So what does this mean? Okay. It's worth sort of stepping back and taking a look at what we're doing here. What we're doing here is we're imagining a general scalar field theory, and we're only interested in the infrared degrees of freedom. And so we integrate over the UV degrees of freedom, and we're left with an infrared theory. And we want to ask, how do the coupling constants change when I look at this infrared theory? And so I need to compare it to my original theory. And so I just rewrote it by rescaling the variables in a way that makes it look like it has the same range of integration over field variables as my original theory. And what you see is that the coupling constants change when you do this. And they change in two ways. They pick up these factors here. So these are genuine factors that come from integrating out the variables. They're things that we have to compute. They take a little bit of work. You have to use Feynman diagrams to compute these. But there's this important piece right here, which tells you that all of the coupling constants scale in a way that's determined by their dimension. Okay. Remember, G is a dimensionful parameter. And so if we rescale our x variable in some way, these G's have to change. And this factor of B to the minus dimension of G is just telling us exactly how they had to change. So in particular, what we see is that as B goes to 0, that is to say, if we're interested in studying the physics deep in the infrared at very low energy, the coupling constants with negative mass dimension will get very small. Whereas the coupling constants with positive mass dimension get very large. So, from the point of view of low energy physics, operators or terms in the Lagrangian where the couplings have negative mass dimension are irrelevant. They just don't matter from the point of view of low energy physics. Whereas couplings with positive mass dimension are going to be important, and so these are usually called relevant. Indeed, we very often, instead, saying coupling with positive mass dimension is a very long phrase. So very often we just say it's a relevant coupling or a relevant operator as opposed to an irrelevant coupling or an irrelevant operator. But the point is that you now see that is a physically important language because it's telling you that if you study low energy physics, it's those terms with positive mass dimension, the relevant terms that are going to be important for low energy, and it's the terms with negative mass dimension that are going to be unimportant. So this procedure whereby the coupling constants change as you integrate out these degrees of freedom in the ultraviolet, this is known as renormalization group flow. Or RG flow. And I think starting next class, we'll hopefully have a chance to compute in a little bit more detail how some of these couplings change under renormalization group flow. It's a beautiful story. You can consider spaces of field theory, and you can consider the flows on the spaces of couplings, and then this will magically pick out for you special points in field space, which are sort of attractive fixed points in the infrared, and those are the theories that we can use to describe all sorts of interesting physics. So for example, this is especially important not just in particle physics, but in condensed matter physics. So for example, if you want to study typically the physics of some material at very low energy, then very often a useful way to do that is to try and make some guess for what the basic degrees of freedom that are active for that system are, and then try and find an infrared fixed point of this renormalization group flow. Good. Okay, sorry for going over time for a few minutes. I'll see you on Thursday.